Hi everybody. So our next topic is optimization, right? And this is going to be sort of an application of either finding the relative maximum or relative minimum, or in some cases absolute maximum and absolute minimum. I think in these problems usually they're going to be the absolute maximum or minimum. And in almost all the problems, it's going to be very specific. It's going to say whether you want to maximize something or minimize something, right? So some quantity, right, that we either want to maximize or minimize, find the maximum or minimum of some quantity, right? So just some examples might be, let's say you have a business and you have a model for the amount of profit you're going to make. That might be a function of the number of units you sell. So once you have that function and you want to maximize your profit, right? So this is something you might want to maximize, right? Or if you have a model for your cost as a function of, again, say the number of units that you're producing, this is something you might want to minimize. Okay. So those are just some examples. Another example might be, let's say you're building a fence, right? So maybe just a rectangular fence around a garden or something. You might want to, right, build the biggest garden, right? You want to maximize the amount of space in that garden, right? And the amount of space is usually area. So in this case, we might want to maximize the area. I can spell maximize the area, right? Yeah, in other problems, you might want to talk about distances between points, right? Maybe the distance along a curve or something. And you might want to find the smallest distance, right? So distance is something you might want to minimize, right? Or maximize. I guess it depends on the particular application, right? So yeah, a lot of these quantities, area, distance, maybe volume as well, these come from geometry, right? Or even angles, right? You might want to find the biggest angle, right? So these are all, in this case, you might have to use trigonometry for angles, right? Sines and cosines. Right, and these are just some examples. There's others, maybe time, the amount of time it takes to get from, say, point A to point B. If you want to take the shortest time possible, this is something you might want to minimize as well. Right, so, yep, that's the whole idea of optimization. Maximize or minimize some quantity, right? And so this is just a basic list of things that you might want to think about when you are trying to find the maximum or minimum, right? So it's a list of guidelines, and when we start out, we're going to start out with some pretty simple problems, but then they get rather complicated. So for the more complicated ones, you might want to think about this step-by-step process, right? And I'll just go through it quickly, right? First, after you read the problem, of course you want to identify all the quantities that are given, right? And, for a rectangle, it might be the perimeter of the rectangle. You might have a certain amount of fence to go around your garden, right? So that might be the perimeter, twice the length plus twice the width, right? So this is also the perimeter. Perimeter, I can spell. So this might be a given, right? This might be, 80 feet, for example, right? So what's the biggest rectangle you can build with the 80 feet of fencing, right? Okay, so yeah. So that might be given, right? And then, of course, there's the quantity that you want to maximize or minimize, right? And that might be area, right? Or profit or cost or distance and so on. Okay, so yeah, so that's what we have so far. So make sure you understand what's given and what your goal is, what you're trying to do, what you're trying to optimize, right? In either maximize or minimize, and that'll be clear in the problem. Right? So then this step 2 is to write down an equation, right? What's called the primary equation of the quantity that's to be maximized or minimized. Okay? And this typically comes from geometry or trigonometry, although it doesn't have to. In fact, it might be an equation that's just given in the problem. So if you're talking about profit or cost, they might supply you that function. But in a case for, say, area of a rectangle, that's something that you probably should know. The area of a rectangle, I'll call it A for area, is just the length times the width, right? So you have the length, you have the width, just multiply them and that gives you the area. Okay, so that might be the primary equation in one of the examples. In fact, we will see an example like this pretty soon. Okay, so the issue here, though, is, okay, so I have the area in terms of the length and the width, right? How do I maximize that? So, right, so to find a maximum or minimum, we need the critical numbers, right? So we're thinking of area as a function of, well, there's two quantities here, length and width. It's just the product, length times width, L times W. Right. But it depends on two variables, both L and W. It's a function of two variables. Okay, and up until now, we've never dealt with that, right? We've never had a function of, say, both x and y, right? It's always been just a function of x, right? That gives you y. So an equation with more than one variable is very difficult to deal with. In fact, there's an entire course on that. Calculus 3, we deal with functions of, say, 2 or even 3 variables. But that's a couple semesters away, right? So we're not going to do that, obviously. So our next step, our step 3, has to somehow involve taking this equation with 2 variables and somehow reducing it down to a function of just 1 variable. Okay? And that's done by, well, again, the parameters of the problem. So in step 3, we want to reduce the primary equation down to a function of just 1 variable, right? It doesn't have to be x, it could be L or it could be W, but it can't be both, right? And so the usual way to do that is to find a secondary equation, another equation, that somehow relates the 2 variables, L and W. Okay, so how are L and W related? Well, again, it depends on the particular problem, but it could be, for example, that we only have a certain amount of fence to go around the garden, right? And so that puts a constraint on how big the rectangle is, because we only have a certain amount of fence. Say we only have 80 feet of fence. Right? So this gives us a relationship between L and W, right? This would be our secondary equation. Right? And based on that, we can either solve for L, right, or for W, and then plug that into the primary equation, and that will reduce it down to a function of, maybe just L or just W. It doesn't matter, right? And then once you have your primary equation down to a function of 1 variable, then you do the usual thing, right? Well, first you find the domain, right? So maybe L can't be infinite, right? It can be maybe between 0 feet and, let's say, 15 feet. That's the biggest length you can get, right? So that might be your domain, for example, for a particular function, right? Then you just find the maximum or minimum, right? The usual way, find the critical numbers, right? And then use the first derivative test or maybe second derivative test to ensure that you really do have a maximum area and not a minimum area, right? And there's no, I don't know if I mentioned this yet or not, but there's no trick questions, right? If it says you want to find a maximum area and you go through the first derivative test and it turns out to be a minimum, well, then you know you did something wrong, right? So there's no trick questions. If it says you want a maximum area, then you want to find the maximum, right? Make sense? So that's the idea, right? That's our goal. And so now let's just look at some examples and let's see how this works in practice. Okay, so here's the first example. We want to find the minimum of the product of two numbers, one of which is 4 more than the other. Okay, so this should be a relatively straightforward problem, right? What are we trying to do? We're trying to minimize the product of two numbers. So what should we call the two numbers? So how about just x and y? Right, so let x and y be the two numbers, right? And the quantity we want to optimize, in this case minimize, we want to minimize what? The product. I'm sure you know what a product is, right? It just means you multiply, right? X times y. So what should we call this? How about P for product, right? So this is the quantity we want to minimize, right? This is our primary equation, right? And you can see that it depends on, well, two things, two numbers, x and y. If you only know what x is, that, if you know x is 8, that doesn't tell you what the product is unless I tell you what y is also. Right? So this is exactly the same situation as, say, the area of a rectangle, as we talked about earlier. Right? It depends on two things, right? It's a function of two variables, both x and y. Okay? So yeah, that's not going to work here, right? But what else do we know? We know that one of the numbers is 4 more than the other. Now, it doesn't say which one is 4 more than the other. It doesn't say, whether x is 4 more than y or y is 4 more than x. And it turns out it doesn't matter. So let's just say x is 4 more than y, right? So x is 4 bigger than y. In other words, right, x equals 4 plus y. Okay. So this of course is our secondary equation. And I think I mentioned that usually it comes from geometry, but not in this case. Now it's just reading, just understanding what it means to be 4 more than the other, right? So I'm just literally writing down as an equation what it says in words. Make sense? So yeah, that's our secondary equation. So now what do we do? Well, now we can write our primary equation like this, right? Right now it's a function of x and y. It's just x times y. But look, I can replace x with 4 plus y, right? Because they're equal. So if I do that, I get 4 plus y, right, times another y. And so if I multiply that out now, I get, oh, sorry, I'm messing up the y's here. That's supposed to be a y. Right. So you can either leave it as a product or distribute the y, right? Y times 4 plus y times y. So 4 times y plus y times y is y squared. So do you see what we've done now, right? This is now a function of just y alone. And that may seem backwards to you, right? Maybe we should get this in terms of x instead of y. Well, right, too late now. This is a function of y. But it doesn't matter, right? We can have functions of y. Usually we write this in terms of functions of x. Right? Or you can just switch x and y. It doesn't matter. But so yeah, so our function now, p of y is just, let me switch the order, y squared plus 4y. Okay. So now this is our primary equation, but it's written as a function of only a single variable. Remember, we want to reduce the primary equation down to a single independent variable, right? We could have used x. It turns out we used y here, right? So yeah, so that's your step 3 here. We've reduced the primary equation down to a function of a single variable. Okay, so step 4, what is the domain of this function? What am I allowed to plug in for y? Well, it just says that, x and y are two numbers. It doesn't say they have to be positive numbers. It doesn't say they have to be negative numbers. It doesn't say they have to be integers, right? They could be fractions or decimals or irrational numbers like square root of 2. So I don't think there's any condition here that y has to be a specific value, right? I would think the domain is all real numbers. Y could be anything we want here, right? Now, in other problems where maybe you're talking about the length of a fence, right? Remember L for the length of a fence. Well, length is a distance, and it can't be negative, right? You can't build a fence that's negative 5 feet long. So, in those types of problems, L might have to be positive. But yeah, in this problem, x and y are just any two numbers. There's nothing that says that, x and y can't be negative or irrational numbers or things like that. So that's the domain, right? That's your step 4 here. And then step 5, find the maximum or minimum. So remember how to do that? You find the critical numbers, right? So what are the critical numbers for this function? Well, to find the critical numbers, we need the derivative, right? P prime of y, or if you prefer, the derivative of p with respect to y. And that should be easy. I'll give you 10 seconds. Actually, I'll give you 5 seconds, right? It's just 2y plus 4. That's it, right? 2y plus 4. So, the critical numbers are where the derivative either does not exist. Well, this exists everywhere, right? You're not going to be dividing by 0. There's no imaginary numbers or anything. So the only critical numbers come from where this equals 0. So solve that equation, and you have your critical number. Yep. Negative 4 over 2, negative 2. So as it turns out, y is negative, right? And, we didn't know that it was going to end up being a negative, but it seems like there's only one critical number, and it happens to be a negative number. Okay. Now, that doesn't answer the question yet, because the question was to find the minimum product of two numbers. So we need the two numbers. We only have one of the numbers. We have y is negative 2. Now, how do we find x? Well, very easy, right? Go back to your secondary equation, right? We know that x is equal to 4 plus y. And if y is negative 2, we have 4 plus negative 2, or 4 minus 2 is positive 2. So this tells us that x has to be positive 2. And those are the two numbers, right? What's the minimum product? Well, multiply, right? The product is just x times y. So that's 2 times negative 2, which is negative 4. Right? So that's the, oh, did I say maximum? I meant minimum, right? We're trying to find the minimum product. The minimum product is negative 4. So this should be the minimum product. Right. Right. And of course, we didn't even have to find x here. The problem wasn't to find the two numbers. The problem was to find the minimum product. And the minimum product is negative 4, right? So this should be the answer here. Let me highlight that in maybe a different color. Right, so the answer is negative 4. Right. And the reason why I say we didn't need to find the x here is because once you know y, don't forget the product can be written strictly in terms of y. So we could have found the product by just plugging in y is equal to negative 2. Right? And that's just y squared, so negative 2 squared plus 4 times y, 4 times negative 2. So that's 4 minus 8, which is, again, negative 4. Same answer we got earlier. Right. So that's it. Well, not quite. Okay, we're not quite done yet. Because remember something here. When we found the critical number, there's only one critical number. Y was negative 2, right? That was our one and only critical number. But remember, we can get a critical number for three different reasons. It could be a critical number because it's the lowest point, right? And the slope is 0, the derivative is 0. But a critical number could mean you have a maximum where the slope is also 0, right? Or it could mean that you have a graph that just levels off like this and is neither a minimum nor a maximum. So which is it? Is it a minimum, a maximum, or neither? Right? Well, I can be rather glib about it and say, well, the question said to find the minimum, so of course it has to be the minimum, right? And in fact, I did say there's no trick questions, so it's got to be the minimum, right? But what happens if we solve this equation and we get two critical numbers or three critical numbers? It's possible that only one of them is a minimum. The others might give you a maximum. Okay, so how do you know which one gives you the minimum or the maximum in some cases? Right. So yeah, first derivative test, right? So let's look at the first derivative test. Here's our, well, in this case, y, right? Y was -2. And we need to plug in -2 into the derivative. Well, no, if we plug in -2 into the derivative, of course we get 0. That's what makes it a critical number. So we have to plug in what? We have to plug in a number less than -2. How about -3? Plug that into the derivative. And what do we get, right? Remember what the derivative was? It was just 2y plus 4. So this is going to be 2 times -3 plus 4. Let me try that again. So yeah, less than -2 is -3. So yeah, 2 times -3 plus 4 is -6 plus 4 is -2. So -2 is definitely negative. And what's bigger than -2? How about 0? So plug in 0 into the derivative and you get 2 times 0 plus 4, which is +4. So that's a positive. So the first derivative test says we're going from a negative slope to a positive slope. And that's definitely a minimum. So no surprise that it gives us a minimum because, well, that's what the question was asking in the first place. And in fact, if we did the first derivative test and it turned out to be a maximum, well, then it's a good indication that we did something wrong. Either we did the wrong derivative test or we plugged in the wrong numbers, or maybe we got the wrong critical numbers. But you got to go back and figure that out then. So this is just a good way to check, right, that the first derivative test tells you that it is a minimum product, right? So there you go, right? Out of all the numbers that you can get where one is 4 bigger than the other, the minimum product is going to be -4, right? If you pick any other two numbers, right, where one is bigger than the other, and I don't know, you just, how about 1 and 5, right? If y is 1, x is 5, what's the product? The product is 1 times 5. Well, -4 is certainly less than 5, right? So this does not give us the minimum product, right? So that's the idea. You pick any pairs of numbers where essentially the difference between them is 4, then the minimum product will be -4. And that's what we determined using this procedure up here. Make sense? Okay, so easy problem to start. Let's do a slightly harder one. Okay, so example 2. We have 2 adjacent rectangular pens are to be built with a total length of 60 meters of fencing. And we want to find the maximum area of the 2 rectangular pens. Okay, so before we try to do anything else here, let's just draw a picture, right? So we have 2 adjacent rectangles. Here's one. Let me try that again. Okay, so here's one rectangular pen, and then we have another adjacent one over here. Yeah, I don't want to be... Right. Oh, and it doesn't say that they have to be identical, right? You can imagine that one is maybe bigger than the other. But yeah, let's keep it simple and say that they both have the same area here, right? Now we want to find the total area, the maximum total area. Okay, so what do we have here? We have the length, which I'll call L, and then we have the width, which I'll call W. And so what do we want to maximize? We want to maximize the total area. So I'll use A for area. And of course, the area of this big rectangle here is just length times width. Oh, and it almost looks like a square if you're not careful. So yeah, this could be a square, but we don't know that for sure. It's just the way that I drew it, right? I could have drawn it this way, right? And then these are the two rectangles. Clearly not a square, right? Or I could have drawn it this way and divided it up like this. Clearly not a square. Okay, so be careful how you draw it. Don't think that that's the way that it has to be. Okay. So again, we want to maximize the product of the length and the width. That's the area. Right? Okay. So what else do we know about this rectangle? Well, that the total length, right, is 60 meters. Right? So what is the total length of this fence? Well, we have this length here, right? So that's L. So I'll write down the expression for the total length. So we have a length L. And if we go the top part of the fence here, right, that's also a length. So we have another length, right? What else do we have? We have a width all the way here on the right. So that's width. We have the dividing line in the middle here, and this should be a straight line. So let me try that again. Right. So that's also part of the fence. So that's another width. And then we have this on the left here. That's also another width. So what do we have total? We have two lengths, so 2L, plus 3 widths, 3W. Okay, so the total length of the entire fence is 2L plus 3 times W. 2 times L plus 3 times W, right? And we know that that has to be 60 meters because that's all we have. That's all we're given. I suppose we can go out and buy more and make it longer, 80 meters or 100 meters, but okay. In this problem, we're only given 60 meters of fence. Okay. So remember, this is our secondary equation here. Right. And it's just based on the geometry, based on this condition. Right. So the primary equation was, of course, this. Right. The area is length times width. Okay. And now I think we can actually, right, reduce the font, right? So step 3, remember, right? So step 1 is to find the quantity to be maximized, right? And in step 2, it's to find the secondary equation. And then in step 3, reduce the primary equation down to a single variable, right? So that's our goal here, right? So here's what we want to do, right? We want to reduce this down to a function of either L or W, right? And it doesn't matter to me. Want to make it a function of just L, right? Or just W. It's completely up to you. Okay? So here's how we're going to do it, right? We're going to have to take the secondary equation and solve it not for L, but for W. Okay? So if we wanted this to be a function of W, you would solve for L. Now that we want this to be a function of L, we have to solve for the other variable for W, right? So let's solve for W here. 3W plus 2L is equal to 60. So subtract the 2L from both sides, and we get 3 times W is equal to 60 minus 2 times L, and then just divide by 3. So W is just, maybe we can split this up, right? 60 divided by 3 minus 2 over 3 times L. And 60 divided by 3 is, well, 20, right? So 20 minus 2/3 L. Okay. So this gives us W in terms of L. And now our primary equation was L times W, right? But now we know what W is, right? It's the thing that I just boxed here. So change the W to 20 minus 2/3 times L. And by doing that, the area is now a function of just L by itself. Right. And so you can see it's very similar to what we did in the first problem. Instead of L times W, it was X times Y. Right. And of course, the other difference is that here we wanted to minimize the product. Here we want to maximize it. Oops, don't know what happened there, but okay. So we want to maximize instead of minimize, right? Okay, so now we do the usual thing, right? Take the derivative of A with respect to L, set it equal to 0, find the critical numbers. And we can do that, but we would have to use the product rule here, because this is a product. Or, just like last time, we can distribute the L, and we would get 20 times L. Oops. So 20 times L minus 2/3 times L squared. Right. And now we can take the derivative pretty easily. So the derivative of A with respect to L, or if you prefer, A prime of L. Right. So this is just going to be 20 minus, let's see, 2/3 times 2 is 4/3 times L. Right. And just like in the last problem, the only critical numbers here come from where, right, this equals 0, right? The derivative will exist for all L, right? So yeah, we're just going to solve this for L, and that's pretty easy. Subtract the 20 from both sides, and divide by negative 4/3, or maybe multiply both sides by negative 3/4. And that cancels the negative 4/3, right? So finally, L is just equal to, let's see, a negative times a negative is positive. So this will be positive 60/4, or 15. Okay, so that's our critical number. L is 15. 15 what, though? 15 meters. We're in meters here, so don't forget your units. 15 meters. Right. And now, the question was to, let's see, find the maximum area. So they're not looking for the length or the width, they're looking for the maximum area. And just similar to the last problem, they're looking for the minimum product. Right? So we can do this two ways at this point. Now that we know L, we know the area as a function of just L was what? It was 20 times L minus 2/3 times L squared. But now that we know L is 15, we just plug that in. We get 20 times 15 minus 2/3 times 15 squared. And I'm going to need a calculator, so hang on. Okay, well, 20 times 15 is 300. And then 15 squared is 225. 225 times 2 is 450. 450 divided by 3 is 150. So I think we get 300 minus 150, and it's 150. Well, 150 what, right? This is an area, so length times width, meters times meters, square meters. So that should be the maximum area. That's the biggest pair of rectangles we can get here, right? So this should be 150 square meters. And the way I drew that doesn't look right, right? 150 square meters. And you can abbreviate this any way you want, right? Square meters. Right. And so the way I drew it, you can say, well, it's 75 square meters for each, because there's two of them. That's fair enough. But the key word here is, right, the maximum area of the two rectangular pens. In other words, the total area. The total area, right? Yep, so that's one way to find the answer. The other way is to go back and find W, right? Now that we know that L is 15, what's W? It's just 20 minus 2/3 of 15. So that's 10. 20 minus 10 is 10 meters. Right? Well, so remember, area is length times width. the length was, let's see, 15 meters, and the width is 10 meters, so 15 times 10, 150 square meters. Same answer, right? Same answer either way. Okay, so we didn't have to find W in this case, but, that's one way of doing it. Okay, and that should answer the question. Find the maximum area. It's 150 square meters. Again, how do we know it's a maximum and not a minimum? Well, maybe we should use the first derivative test. Actually, we did that in the last example. For my money, this is a lot easier to just use the second derivative test. So remember the second derivative test? Derivative test. Right, so remember the area is a function of L. I almost forgot this, right? 20L, 20 times L minus 2/3 times L squared. And we took the first derivative, right? So the first derivative was, 20 minus 4/3 L. There we go, right? 20 minus 4/3 L. And so to take the second derivative really is not that hard here. The derivative of 20 is 0. The derivative of negative 4L is just negative 4/3 times L is just negative 4/3. So we get negative 4 over 3. What does that tell us? Well, remember when the second derivative is negative, that means your graph is concave down at your critical number. The critical number here for L, remember, was 15. So this is the area as a function of L. And so at your critical number, if this is concave down, that tells me that this gives us a maximum area, right? So yeah, once you have the first derivative, if you find it's pretty simple to take the second derivative, that's usually a little bit easier than, plugging in, say, 14 and 16. You have to plug both those numbers into the first derivative and then compare them, right? As we can see from the graph here, if we plug in 14 into the first derivative, it'll be positive, right? Because the slope of the tangent line is positive here. And then if we plug in 16, we'll see that it's negative. And so by the first derivative test, if we go from a positive to negative, that's the sign of a relative maximum. So once again, we confirmed that the question was accurate. We want to find the maximum area, and we did that. The maximum area is 150 square meters, and it occurs when the length, just to complete the answer here, the length is 15 meters, and the width is 10 meters. So again, I drew this a little bit funny here. It's a little bit longer than it is wide here. Yep. And in fact, this is just, 7.5 meters for each one, and 10 meters for the width. Right. But yeah, that'll give you the biggest rectangle based on the three parts to the rectangle, the two lengths and 3 widths. Okay, so again, a very typical problem for optimization. Okay, so I think I'll do one more. So we did one minimum, we did one maximum. I guess I'll do a minimum. How's that? Oh, and I got to start over. So give me 1 second and I'll pull up a third problem. Okay, so here's our next example. I guess this is our third, right? I said third example, so we'll call it example 3. And seems simple enough, right? Find the point on the line y equals 3 minus 1/2 x that's closest to the origin. Okay, so how are we going to do that? So, well, if it's not clear, maybe draw the picture, right? Let's draw the graph. Okay, so let's see, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. And then the line, 3 minus 1/2 x, right? So the y-intercept is 3. And if x is 6, y is 0. So just connect these points with a straight line. Right? The line keeps going both directions. Right? So this is just the equation of the line, y equals 3 minus 1/2 x, or if you prefer, the other way, y equals negative 1/2 x plus 3. So the y-intercept is, right, 0, 3 here, and the slope is negative 1/2. I think that's clear from the graph, right? All right, so what do we want? We want the point on this line that's closest to the origin. Right? Now, where's the origin? The origin is 0, 0. Right? That's this point right here. Notice that point is not on the line, obviously. Okay. So out of all these points on this line, which one's the closest to the origin? Right? So is it this point over here? Is that the closest we can get? What about this point over here? That looks like it's a little closer, doesn't it? Right? Is it this point way over here, where x is 7? Definitely not, right? That's not, right? That's much further away than this point. So yeah, what are we trying to do here? What we're trying to do is minimize a certain quantity here. And that quantity is the distance between the origin and, well, this point. Right, so we're trying to minimize the distance. Right? Right? If you want to get closest to something, right? You want to get as close as you want to something, you decrease the distance, right? The closer you get, the shorter the distance. So yeah, that's why this problem is a little deceptive here, right? It's not clear that, we're trying to minimize the distance. It doesn't say find the point which minimizes the distance. That might make it clear, but again, some questions are not that obvious. So this one, you really have to read into the question. What do you mean by the closest point to the origin? You mean the one that gives you the shortest distance between the origin and the line. And this one looks pretty short, right? That might be it, actually. But again, this one here, yeah, that looks a little longer. The point is, you're not going to, unless you draw a really good line here, a really precise, careful line, you're not going to get it by just looking at the graph here. You might get a good idea, like you might say, oh, it might be when x is 1, or maybe when x is, 1.2 or something. But now we're just kind of guessing, right? So yeah, we want to make this much more precise here, right? So what's the distance between, I can spell distance, right? The distance between 2 points, one of them is just 0, 0, the origin, and the other is a point on the line, xy. But x and y could be any point. It could be this point way up here, right? Or this point, or this point, or this point, or this point. But none of these points are on the line. Okay, so we're not trying to minimize the distance of any point. In fact, the answer to that would be 0, right? What point is closest to the origin? It's the origin itself, right? But again, the origin is not on the line, right? Yeah, so we're trying to minimize the distance between 2 points, one of which is 0, 0, and the other has to be on this line, in which case the y value here can't be just anything. It has to be this, because this is what describes the line. You see that? So, right, so now the 2 points are 0, 0, and x, but then y is actually negative 1/2 times x plus 3. Okay. And maybe I was getting a little ahead of myself, right? The distance between 2 points, you should know that's just the distance formula. Right? So the square root of x2 minus x1 squared plus y2 minus y1 squared. Right? And in this case, right, this could be my x1, y1, and then this could be my x2, y2. And what we get then is just, well, x minus 0 squared plus y minus 0 squared, or it's really just the square root of x squared plus y squared. Okay. So that's the distance between the origin and the point xy. But notice, of course, it is a function of two variables. It depends on both x and y. Okay. So what we should do, of course, is replace y with this expression here. Right? In other words, this equation up here, maybe we didn't realize it at first, but this is our secondary equation. This is the equation that relates x and y. And this, of course, this is the distance. This is the thing we want to minimize. And so this is our primary equation. And so in step 3, we reduce the primary equation down to a single function of, in this case, just x. And we can do that, of course, by replacing y with what it equals. Again, this equation up here, this is negative 1/2 times x plus 3. The whole thing squared, right, because it's y squared. So don't forget the square here. And already you can see that this is a function of just one variable, x. Maybe not a very nice function, but so before we take the derivative, right, before we figure out the critical numbers, we might want to maybe expand this out and simplify it a little bit. So let's do that now here, right? So this is going to be the square root of x squared plus, and then when we expand this out, we get negative 1/2 x times negative 1/2 x is positive 1/4 x squared, right? And then we get negative 3 over 2x plus negative 3 over 2x is just negative 3x. And then plus 3 times 3 is 9. Okay. So just simplifying, right, expanding this out, right, term by term, you get this. And then 1x squared plus 1/4 x squared is really 5 over 4 times x squared minus 3x plus 9. Right? And there's our function of x by itself. Okay, so I think that's step 3, right? We took our primary equation, and by substitution, by substituting the secondary equation up on the upper right here, which of course, that secondary equation was, you know, no mystery here, was given in the problem, right? This is the secondary equation here. Okay, so in some cases it'll be given to you. In other cases it won't be. You'll have to find it based on the reading of the question that they gave you. Okay, so far, so that's our step 3. Now just take find the critical numbers, take the derivative, set it equal to 0, and so on, right? Now before we do that, I think I skipped step 4 here, and I did that in the previous problem. And in some cases it's not really going to matter what the domain of the function is, and I don't think it's going to matter here, right? But the domain of this function is, well, any value of x that makes this quantity greater than or equal to 0. Right? So to find the domain properly, we would actually have to solve this inequality. And personally, I don't feel like doing that. It involves solving a quadratic equation. And for the most part, it's just not necessary here. Right? Excuse me, what could x be? Physically, right? If you look at the line up here, right, what could x be? Well, it looks like it's going to be somewhere around 1, right? Maybe 1, 1.5, maybe 2, right? So somewhere between 1 and 2 it looks like. But that's only because, you know, we're looking for the minimum distance, and that's what it looks like. But this point could be anywhere on the line, right? So really x could be any real number. There's no reason to think that x cannot be negative or that x can't be a really big number. It's just that if x is a really big number, then that's clearly not going to give you the minimum distance. It's going to be a very big distance, right? So, yeah, but in terms of the actual function, I think x could be anything. which means that that inequality, I'm guessing, oops, the one that I just erased here, is probably true for all real numbers x. Right? In other words, that's the graph of the function here will always be above the x-axis. So this will be true for all x. I don't know that for sure, but it does seem to make sense that you're not going to get any imaginary numbers. After all, the square root of x is a distance, and the distance can't be imaginary. Okay, so yeah. Now, again, step 4 here will become important in other problems where it might be clear that x might be not all real numbers, right? Maybe x has to be from 0 to 7 or something like that. Right? And the reason why that's important is because, remember, when you're finding the absolute maximum and minimums, you have to plug in the endpoints into the function. Because the maximum or minimum, while it could occur, right, at a critical number in between, it doesn't have to. Right? If the graph looks like this, then, well, A, there might not be any critical numbers, but then B, your maximum would be at one of the endpoints, and your minimum might be at the other endpoint. Okay. So even if you do have a critical number like this, and you're looking for the maximum, well, it's not going to be at the critical number. It'll be at the left-hand endpoint here. So that's where the domain becomes important. But in a lot of problems, it really isn't, and in this problem, that won't come into play here. Okay, so with that said, I think we can go on to the last step. Step 5, find the absolute maximum or minimum using calculus. So again, we just take the derivative and set it equal to 0. So what's the derivative of d? And I'll write it d prime of x, because if you write it this way, boy, that looks really awkward. dd over dx. Yeah, so that's the problem with using d for distance. But this is fine, right? D prime of x is the derivative of x, right? So how do you find the derivative? Well, the way I would do it is, let's rewrite this in terms of the exponent 1/2, so we can use the power rule, right, along with the chain rule. 5 over 4, x squared minus 3x plus 9, all to the power negative 1/2, right? And then this is the key step here, right? Don't forget the chain rule, because if you forget the chain rule, you're not going to end up with any solutions to this equation, right? So the chain rule is the key here. So when you take the derivative of what's inside the parentheses, I think we get 5 over 2 times x minus 3. So that's what we set equal to 0 now, right? Oh, and where does it not exist? I think this derivative will exist for all x. Again, I don't know that for sure, but I suspect that it is, just based on the fact that the square root will not be 0 or negative, right? So yeah, if we rewrite this in the more familiar form here, 5 over 2 times x minus 3, all divided by 2 times the square root of 5 over 4x squared minus 3x plus 9. Where does this equal 0? Where the numerator is 0, right? We can effectively ignore the denominator here, or multiply both sides by the denominator, and that part's just not going to matter. So when you solve this equation for x, you get 5 over 2 times x is equal to 3. So multiply by 2 over 5. And we get that x is 6 over 5. Right? Or if you like decimals, 1.2. And so going back up to the picture, oh, I think I almost guessed that. I think I did say 1.2 at once, right? But I didn't know that for sure. It could have been 1.3 or 1.4. All we know for sure is that it's probably somewhere between 1 and 2. And so this answer, 1.2, makes perfect sense in terms of the graph here. That when x is 1.2, right, that's going to give us the minimum distance. Right? Or maybe the maximum distance, right? We don't know that yet. So we'll use the first derivative test or the second derivative test to confirm that. before we do that, though, let's answer the question. The question is to find what? To find the point on the line. The point on the line. Remember, a point is not a number, but a pair of numbers. It's an x and a y. So far, we just found x. So how do we find y? Well, remember, y is a point on the line, and the line is given by the equation y equals 3 minus 1/2 x. So y equals 3 minus 1/2 x. That was given in the problem. But now, just replace x with 1.2, or I'm going to use the fraction 6 over 5. So this is going to be 3 minus 3 over 5, right? Which is what? 15 over 5, right? Minus 3 over 5, which is 12 over 5. Or as a decimal, right, 2.4. Okay, so this is your y, right, and this is your x. So to answer the question, the point, right, on the line, y equals 3 minus 1/2 x, nearest or closest to the origin, 0, 0, right, is the point. Well, either way, 6 over 5, 12 over 5, if you like fractions, or you can just say 1.2, 2.4. And there we go, right? So that point is closest to the origin. Or is it? Is it, right? Because what are we trying to do? We're trying to minimize the distance. And when we solve this equation, we got our critical number, right? X is our critical number here. But that doesn't mean it's a minimum. It could be a maximum, or neither. The only way to know for sure is, well, use the first derivative test or the second derivative test. Okay, so what can we do here? Well, remember, here's the derivative. Do we want to take the second derivative? I don't, right? I mean, look, this is a product, so we need the product rule. We also need the chain rule again. So this does not look like a pleasant calculation to take the second derivative for, right? So for that reason, I think I'm okay with just using the first derivative test. So here's x. Here's our critical number, 1.2. So what do we plug into the derivative here? Something less than 1.2, right, like 1. Or how about 0? Right, x can be 0. So if we plug that in, what do we get? We get, negative 3 divided by the square root of something. Negative 3 divided by 2 times the square root of what? The square root of 9, right, which is 3. So I think we just get negative 1/2, right, which means it's negative here. Right, we know it's 0 at 1.2. That's what makes it a critical number, right? And so what happens if we plug in a number bigger than 1.2, like 2, right? So plug that into the derivative. Again, be careful you don't plug it into the original function. We're not looking for the distance here. We're looking for the derivative, right? The slope of the tangent line at 2. And so the numerator is, it's not negative 3 anymore, right? When x is 2, it's 5 minus 3, which is positive 2. So the numerator will be positive 2, and the denominator will be 2 times the square root of, 2. So 4 over 4 is 1. 5 minus 6 is negative 1. Negative 1 plus 9 is 8. I just want to make sure. 5 minus 6, yep, negative 1. Negative 1 plus 9 is 8. So the square root of 8, right? So 1 over the square root of 8, well, whatever that is, it's a positive number. So by the first derivative test, we're going from a negative slope to a positive slope, which tells us we have a minimum, not a maximum. And that is the shortest distance, or the minimum distance, between the point and the line, the origin and the line, right? Okay, so again, the answer is the point, and you can write it either way with decimals or fractions. That's a 12, right? Yep. Now, in another question might ask you, what is the minimum distance? What would the minimum distance be? So, yeah, you can just find the distance between these 2 points. And in fact, that's just the square root of x squared plus y squared. Right? So that's the square root of 1.2 squared plus 2.4 squared. I guess I'm going back to decimals here. And I get 7.2 under the square root. So the square root of 7.2, which is, well, it's approximately 2.683, right? But again, that's approximate. This is the exact answer. And maybe we can write it as a decimal. It's the square root of 36 over 5, right? Or just 6 divided by the square root of 5. So either way, this is the exact answer. And then this is the approximate to 3 decimal places. So that tells us the actual distance. And, well, that looks about right. That doesn't look too bad, right? It's a little more than 2.5 units, right? So if this is 1 unit, this is 2 units. It's not quite 3 units, right? So yeah, this is about 1 unit, this is about 2 units, and then a little more than halfway. So close enough, I guess. Again, they didn't ask for the minimum distance, but in problems where they ask for the minimum distance, it's just plugging in the numbers into the distance function here, right? Okay, so that's how this works, to find the minimum distance. And yeah, how about one more? Okay, so this is, I guess, our example 4. And I would consider this to be a bit more difficult, a bit more challenging than the other 3. Because it's a little bit more geometric, right? So we're going to have to rely on some of the geometry formulas that are in the back of the book, right? So yeah, so example 4, we want to find the volume in terms of R of the largest cylinder that can be inscribed in a hemispherical dome of radius R. Okay, so what does that mean, right? So we have a hemispherical dome, okay? So remember, that's half of a sphere. So pretend this is my hemispherical dome. Close enough, right? And the radius is capital R. Okay, so that's given. And what do we want to do? We want to inscribe. So what does inscribe mean? We want to place inside the dome here a cylinder. Okay, so now there's a lot of ways I can do that, right? I can take a very thin cylinder at the top here, make it like this. So that's inscribed inside the dome, right? Or I can take a very short cylinder, something like this, that just fits inside, right, like this. So that's also a cylinder, a very flat cylinder. But the question is to find the volume of the largest cylinder. Okay, so largest cylinder has what? Has the biggest volume, right? So the biggest cylinder that can fit inside the dome. Maybe something like this, right? I think this one's a little bigger than either the flat one or the tall one, right? Or a thin one. So I messed this up completely here, but you get the idea, right? Which of these cylinders is the biggest one? Okay. So yeah, let's say it's somewhere in the middle. Let's say it's this one here, right? Pretty tall, but also pretty wide as well. And that doesn't look right. Looks a little better, right? Okay, so what determines which cylinder we have here, right? So the largest cylinder, right? The one with the biggest volume. So what's the volume of a cylinder? Okay, so this is one I'm hoping you know, but if not, don't panic. Just look in the back of your book, right? And of course, there's two things you have to know. You have to know the radius of the cylinder, which I'll call little r. Now, you might think, wait a minute, I thought the radius was capital R. Don't get confused here, right? There's two things going on here, right? There's the cylinder. Let me just pull that outside the dome here. So if I just move this outside the dome, it's the same cylinder, I just moved it around. What's the radius of the cylinder? It's this distance, right? It's from the center to the edge of the cylinder. It's not the same as the radius of the dome, right? Which is much larger. So that has a bigger radius. Okay, so that's why we have to use a lowercase r for the radius of the cylinder, not the radius of the dome. Okay. What else do we need? We also need the height of the cylinder, which we can just call that h for height. So volume of a cylinder, radius r, and height h. Okay, so if you don't know it, look it up. It's oops, sorry. I almost forgot myself. Yeah, it's just pi r squared h. So pi times r squared times h, right? So that's the formula for the volume of a cylinder, right? And again, they didn't give that to us in the problem. If this were on a test, you know, I would give that to you. You know, because you know, you may or may not be able to look that up on a test, right? So yeah, for the homework you can look it up, but for a test, if it's in class, you're not going to be able to look it up. If it's an online test, you can do whatever you want. Of course, you can look it up, right? But again, just for convenience, that'll be in the problem. All right. So what do we want to do? We want to find the largest cylinder, right? So we want to maximize the volume. This is something we want to maximize. And how do we maximize something? Find the critical numbers, so take the derivative and set it equal to 0. But again, we have the usual problem. This depends on two things. It depends on the radius and the height. Right? It's a function of two variables, r and h. If you increase the radius, you increase the volume. If you increase the height, you increase the volume. So the volume depends on two quantities, right? Pi is a constant. It does, right? So pi is just a number. But r and h are variables. Okay, so yeah, so we cannot take the derivative of a function of two variables, at least until you get to multivariable calculus, calculus 3, but we're not there yet, right? So somehow we have to reduce this down in step 3 here to a function of just two variables, and so we need a secondary equation. So let's find our secondary equation, right? Oh, yes, this here is our primary equation, and in fact, I didn't have to write it twice, did I? Yeah, we know it's a function of two variables, right? So yeah, good enough. Yeah, so this is our primary equation. Primary equation. And now we have to find our secondary equation. Now, if you remember in the last problem, it was basically given to us, right? It was the equation of the line y equals 3 minus 1 half x. Okay, but it's not given here, right? It's not clear in terms of the question what the secondary equation is. Okay, so let's think through this carefully, because this is the hard part here. How do we come up with a secondary equation, right? So what are we looking for, right? We're basically looking for a relationship between r and h. So how are r and h related, right? Or are they? I mean, you know, it looks like for the cylinder, we can draw a thin cylinder like this, right, to make h bigger and r smaller. Or we can have a very flat cylinder to make h very small and r very big. And it doesn't look like there's a very clear relationship between r and h. Okay, So the key thing here is that this cylinder can't be just any cylinder, right? I can't make the cylinder like this. Why not? Because it wouldn't fit inside the dome here. It's too big. There's no way it can fit. Okay, it's too big. So likewise, oops, I erased the H here. Right, likewise, I can't make the cylinder this tiny either, because even though it will fit inside, it won't be inscribed, right? It won't touch the top and the bottom at the same time. You can fit the cylinder down here, but it's too far from the ceiling of the dome. Okay, so we want one that fits, just fits inside. It touches the top of the dome and it touches the floor, which is just the disc down here, right? So there you go, right? There's a sort of, right, you're fighting between increasing H and decreasing R, and I showed you this before, right? You can make H bigger but R smaller. We can make R bigger and H smaller, but we can't make them as big as we want because then it won't fit inside the cylinder. Okay. So here's the key, right? The key is to draw the radius of the cylinder, because I drew the radius this way, and it turns out that's not very useful. Not very useful to draw it that way. Okay. So here's how I'm going to draw the radius of the, not the cylinder, but the dome. I'm sorry, the radius of the dome. Right, because I drew it this way, but here's what we want. We want, right, the center of the cylinder to also be the center of the dome. And this should be a straight line because it's a radius, it's a line segment. I'm having a hard time. All right, that's pretty good. That's a straight line. Okay. So this is also the radius of the dome, not the cylinder. Right, the cylinder has radius little r, and the height is capital H. And there you go. There's the relationship. So write it down, and that's your secondary equation. Everyone got it? I hope you got it. Okay, if it's not clear, here's a hint. And maybe you didn't see me doing this. So let's draw this out here. Right, here's capital R. Here's little h, and here's little r, and what I drew here was a little right angle. How do I know it's a right angle? Well, the floor is flat, and the height is vertical. So you have a horizontal line and a vertical line. Of course, they're perpendicular, right? They're at right angles. Okay, so I hope that helps, because what I drew here, of course, is a right triangle. And what do we know about right triangles? Pythagorean theorem, right? Now in this case, A is little r, B is little h, and C is capital R. Right? So there you go. There's our secondary equation. Let me just copy it down up here. Okay. This becomes our secondary equation. And we get that based on the geometry of the problem, the fact that the cylinder is inscribed in the dome. Right? That this point of the dome up here is also touching the cylinder, the top of the cylinder up here. And so that's what gives you this little right triangle. The radius of the dome, right, sort of becomes the diagonal of the cylinder. Does that make sense? Yeah, like I see, if you have to draw it correctly. If you draw it, you know, if kind of sloppy, then this might not be obvious, right? It's certainly not obvious if you just draw the cylinder by itself. How do we know that this is the radius of the dome, right, unless we draw the dome with it? And I'm not going to try to do that because I did it over here, right? Okay, so there you go, right? This is our secondary equation, right? Secondary equation, and this is our primary equation. Now you know what to do, right? Reduce the primary equation to a secondary equation by substitution. So we're going to plug this into the formula for volume, and that'll give us a function of just one variable. Okay, and what should that variable be here? Should it be as a function of r or as a function of h. Right. You can do it either way, right? In some ways it just doesn't matter. However, one way is a lot easier than the other. Right? And just look at the primary equation. Look what we have here. We have r squared. What do we have in the secondary equation? We have r squared. Right? So if I solve for r squared, all I have to do is take away the h squared from both sides. Right? So I get little r squared is equal to capital R squared minus h squared. Okay. And this I can just replace r squared with. Right? So when I do that, I get v. Oh, I should maybe keep it in green for now. For the primary equation, will be in green. So we have pi. Now r squared is also, or little r squared, is capital R squared minus h squared times the h that's on the outside, right? So yeah, the easiest thing to do is to write v as a function of little h. Okay. So yeah, now remember, capital R is given. Capital R is a constant. Right? The radius of the dome is a constant. Right. And in an easier problem, they would probably just give you a number. They would say, you know, find the volume of the largest cylinder inscribed in a dome of radius 14 centimeters, right? Or 200 inches, or 5 meters. Okay, so R would just be some constant, right? It could be a number. In this problem, we don't know what that capital R is, but the radius of the dome is fixed, right? We can't get a bigger dome or a smaller dome. That's the given size of the dome. So the capital R is a constant. This is only a function of little h. If you insisted on writing this as a function of R, well, we can do that, but we have to solve for h here. H squared is going to be r squared minus, or capital R squared minus little r squared. But then h, of course, is the square root of capital R squared minus little r squared. So this would be pi r squared times the square root of capital R squared minus r squared. Okay, so you could have done that. And there's no problem with that. That's your primary function as a function of just little r. But I hope you see why, personally, I prefer this. Because what's our next step, right? Our next step is, well, find the domain. And, well, right, so both h and r have to be between 0 and capital R. Okay. So that's the domain of either one. Again, usually something you don't have to worry about, but it might come into play in some problems. So on to step 5, find the maximum or minimum of these functions. I mean, you don't have to do both, you just do one or the other. So what's involved in finding a maximum? Finding the critical numbers, right? How do you find critical numbers? Take the derivative. So which would you rather take the derivative of, the green one or the purple one? So the purple one, well, the way they're written, they both involve products, so you need a product rule. But the purple one involves a product rule and a chain rule, right? And you have to probably write this with an exponent of 1/2. And it's kind of a mess, right? So if it's all the same to you, I would much prefer to use this one. And while we're at it, why don't we distribute the h here? So this is going to be pi r squared times h minus pi times h cubed. I mean, I didn't have to distribute the pi, but we might as well, right? So now we don't even need the product rule anymore. We just need the usual rules, the difference rule, sum rule, and then the power rule, right? Remember, capital R is a number. So when you take the derivative, don't do 2 times pi r, right? The variable here is not capital R. The variable is h. Capital R is a constant. So the derivative of this constant times h is just this constant. minus, and then now pi is a constant, and the derivative of h cubed is 3h squared. Right? So I think that's the derivative of v with respect to h, right? Also known as v prime of h, if you prefer to write it that way, right? All right. But what do we do with the derivative? Well, we're looking for the critical numbers, right? Critical numbers are where the derivative is either 0 or does not exist. And again, here's another problem where the derivative clearly exists for all h. Doesn't matter what h is, right? You're not dividing by 0. There's no square roots. There's nothing funny going on, right? So the only critical numbers come from where this equals 0. Right? And what are we solving for? Well, the variable is h, so we're solving for h, right? Solve for h. And that's just a little bit of algebra. I think you can all handle that. So, take 30 seconds and solve that equation for h. Right? So divide both sides by 3 pi. So that gives us that h squared is equal to, the pi's cancel, 1/3 r squared. And so when you take the square root, h is going to be r over square root of 3, or if you rationalize the denominator, you can do r times the square root of 3 divided by 3. I don't think that matters. Yep, again, I'm not picky about which form you choose here. But it is conventional to rationalize the denominator, so it's a good idea to at least do it both ways. Okay, so that's a critical number, right? In fact, that's the only critical number. Oh, you might complain, wait a minute, whenever you take the square root, right, isn't there a plus or minus? True enough, right? But what does it mean for h to be a negative number? You have a height, the height of the cylinder is negative, right? That you measure the height of the cylinder, yeah, that doesn't make sense, right? It can't be negative, right? The radius can't be negative either. So even though we do get two solutions here, one positive, one negative, the physical nature of the problem is that the negative answer doesn't make sense. So we're just going to use the positive, right? Oh, here's another reason, right? Remember we talked about the domain. Both h and r are positive, right? They're between 0 and r. So it's just based on the domain of the function that h cannot be negative, right? And little r can't be negative either. Okay, so yeah, so there's really only one critical number. We're ignoring the negative one. Doesn't make sense for the problem. Yeah. Now, you might think, wait a minute, how can it be a critical number when it depends on capital R? Well, remember, r is just a fixed constant, right? So sure, if r is 3, then you get square root of 3. If r is 12, you get 4 times the square root of 3, right? So it does depend on capital R, but whatever capital R is, we're just leaving it as a constant. So yeah, we can think of this as a critical number, even though it depends on R. Critical number. Okay, so what are we trying to do here? We're trying to find the volume, right? So we could plug this into the equation for the volume here, which is, yeah, it's the one, that I circled here on the left. Yeah, maybe let's just copy it down again. So the volume is pi times capital R squared minus h squared times h. Or maybe better yet, put the h in front. Okay. Either way, doesn't matter. And then just plug in the h, right? Just plug in the h, and that'll tell you the volume. Now you might say, wait a minute, how do we know it's a maximum volume and not a minimum volume? Well, you can use the first derivative test or the second derivative test. Personally, I think the second derivative test is going to work beautifully here. You'll see why. So take the second derivative of v with respect to h, or v double prime of h. right? Remember, capital R is a constant, so the derivative of pi r squared is not 2 pi r, right? R is a number, so the derivative of a number is 0. The derivative of a constant is 0, right? The only variable here is the h. Okay, right? So, yeah, so 0 minus 3 pi times the derivative of the derivative of h squared is 2h. So we just get negative 6 pi h. Okay, and now technically we have to plug in this number for h here. So h is, let's just do r over square root of 3. And when we plug that in, we get negative 6 pi times r divided by the square root of 3. Now capital R is a constant, but it's a radius. It's not negative. So that means we have a negative 6 pi times a positive r over square root of 3. That's definitely a negative number, right? So what happens if the second derivative is negative? It's concave down at the critical number, right? At the h. And so we have a maximum. Right? So we have a maximum volume. And again, that's what the question says. To find the largest cylinder, that means we're maximizing the volume of the cylinder. Okay, so what is the maximum volume? Now we have to answer that question. So we find the maximum volume, right? Not of the dome. We know what the volume of the dome is, right? So don't make that mistake. Find the maximum volume of the cylinder. Right. And again, we have the formula for that. Oh, yeah, it's right here, right above it, right? So this is the volume of a cylinder of height h, pi times h, times capital R squared minus h squared, right? Or you could distribute the h. I don't think it matters here. So what are we plugging in for h? Well, this number right here, or if you prefer, this number. I like the first way, even though it has a non-rational denominator. You'll see why in a second. So this is going to be pi times r over the square root of 3 times r squared. So that's r squared over 3, right? Remember, you're taking the square root of 3 and then you're squaring it. So the square root of 9 is just 3. Okay. Minus, oh, I'm sorry, that's r squared. R squared is fixed. R squared is constant. So that's just r squared. Here's where we plug in h, right? So now, yeah, h squared is r squared over 3. There we go. Yeah. So r squared, leave that alone. That's just a constant. But h is now r over radical 3, r over square root of 3. So let's just simplify this a little. We have pi times r divided by the square root of 3. And then notice we have 1 minus 1/3. So that's 2/3 times r squared. That's just parentheses here. And so what are we left with? In the numerator, we have a 2 times a pi. R times r squared is r cubed, all over 3 times the square root of 3. Okay? And that is the maximum volume. If you insist on rationalizing the denominator, I think at this point we might want to do that. We have 2 pi square root of 3 over 3 times 3 is 9 times r cubed. Right. So this represents the maximum volume of the cylinder. Okay. So that answers the question. Find the volume in terms of r, right? So yeah, again, we don't know what capital R is. Obviously, if they gave that to us, if they said, capital R is, 1 foot, then R is 1, and then this is your volume in terms of cubic feet, right? If R is, 20 centimeters, then you take 20 cubed, I think it's like 800,000 or something, 80,000, 80,000. Well, whatever it is, you just plug it in and you get your volume. But we were never told what capital R is. We just left that as a constant. And so this is the volume in terms of that constant, capital R. Again, what is capital R? It's the radius of the dome, not the cylinder, but the dome, right? It's that number here, that radius here. Okay. Yep, we already established that it is a maximum. We used the second derivative test, so that tells us that this wasn't a trick question. We're not finding the minimum volume, we're finding the maximum volume. Anything else? Like I say, we didn't have to do this in terms of h. We could have done this in terms of r, but taking the derivative of this up here probably would be a little bit more difficult just because of the square root and the chain rule and all that. Once you expanded this out, right, finding the derivative of this really wasn't that hard. So, so one way in this case was, I think, easier than the other way. But eventually both do give you the same answer. Again, doing it this way probably is a lot more algebra and, easier to probably mess up. So, yeah, so I hope this helps. Like I say, this is a more difficult problem, and there might be one like this in the book or in the homework. So yeah, this one's a bit more challenging, but I don't think it's unreasonable. It's just very tricky, and you really have to draw the correct pictures here. And the book is very good with doing that. For the homework, the book gives you the picture, and they label everything pretty clearly. So if I gave you these pictures here, then I think it would be a very reasonable problem. I don't think it would be that difficult, Not saying it's easy. This is not easy, but with the picture, with the labels and everything, I think it becomes a little bit easier. Without the picture, yeah, then you have to draw the picture yourself, and that makes it a little bit trickier. So I would get used to drawing the picture, even if it is in the book, or even if it is, given to you in WebAssign. Draw your own pictures in some cases. So that does help at least figure out the primary and the secondary equations, because neither of those were given in the problem here. We had to figure out what was the primary equation, what we're trying to maximize, and that's volume. Volume of the cylinder, right? Not the dome. And then the secondary equation, this was rather tricky, right? This involved this picture here in terms of this right triangle here. Because, yeah, without that, finding the secondary equation would have been a bit of a hassle. So, yes, like I say, not all of these problems are going to be easy. Some really have, you really have to think a bit. And this is one of those. Okay, so I think that's going to be it for this video. I will make a second video with even more difficult ones. But I figured, the first three I think were fairly routine. The fourth one was a little bit more difficult. But yes, they get even harder than this. So we'll do that in a second video.